Okay, welcome to week 9 of problem solving session for the course Introduction to Wireless and Cellular Communications. Question 1. Consider system with one transmit antenna and L receive antennas, independent noise distributed as Cn of 0, n0 corrupts the signal at each of the receive antennas. The signal has a transmit power constraint of P, and suppose the channel is constant, if the L received signals are added to obtain a composite signal, what is the normalized capacity of the channel? Okay, capacity is for single receive antenna, Capacity is log of 1 plus p over n0. Now we have L receive antennas. Received signal at any one of them is yk given by transmitted signal plus noise. Transmitted signal is same for all the antennas. Noise added for kth antenna is nk. Now we are actually adding all the received signals to get a composite signal. But the transmitted signal is same for all k antennas, so this is simply Lx plus summation nk, k is 1 to L. The noise distribution is independent and given by Cn of 0, n0. Now this looks like y is equal to x plus n, a signal plus a noise component. So this signal the expression looks similar to the situation with one transmit antenna and one receive antenna. So instead of transmitting x, you transmit Lx. So the signal power is variance of the input. Variance of x is p, variance of Lx is L square times variance of x, L square times p. So this looks like a single AWGN channel with transmit signal power L square p and noise variance L times n0. Because the noise is independent. The variance of the sum of noises is simply the sum of the variances. So the Overall noise power is simply the sum of noise power of each of the noise signals. So the capacity would be log to the base 2 of 1 plus transmit signal power by noise variance. Okay, that is the answer. Substitution, please substitute and match with the options that you can do. I'll write down question 2 and 3 for the sake of completeness, but I will not give you the answers since they are simply true or false questions. So I'll give you a few minutes to think about the answers, and then you can write the answer if you know it in the chat box. I won't tell you if it's correct or not, but you can at least discuss among yourselves. Okay, Ashita says question 2 is true. Hmm. Can you go back and check once again? I feel like direct sequence has a wider bandwidth. You should go back and check again. Okay? People will complain if I directly give you the answer, but you should really go back and check again. Question 3, channel inversion does not require CSI transmitter. You will have to go and see the block diagram. Channel state information. Do you need it to? I feel that you do require a CSI. You should go and check in the lectures. Then we will move to question 4. Which of the following power allocation schemes need CSIT? Water filling, channel inversion. Capacity with outage. Both A and B. So here it is obvious that capacity with outage you don't need CSIT. So you don't really need to know any information about the channel characteristics at the transmitter side. If you allow outage, so when you are given capacity, with the possibility of outage. What about water filling and channel inversion? So if you want to do channel state inversion, you should know the channel state, right? And for doing water filling also, you should know how the noise is distributed, right? Think about it. So it's definitely not C. Is it A, only A or B, or is it both A and B? That's a CSIT, not CSIR. So at the transmitter, you need channel state information. For the next few questions, we have this diagram. Consider the following image. It shows curves for capacity with full channel inversion, truncated channel inversion, optimal power allocation, and AWGN capacity. I'll draw the figure uh, roughly. And the question 5 is, which of the given curves is most likely to be the one for capacity with full channel inversion. Question 6 is, which of the curve is most likely to be the one for capacity with truncated channel inversion. Question 7 is, which of the given curve is most likely to be the one for capacity for AWGN. So the capacity for the AWGN channel is the maximum achievable capacity. Then these other capacities are used by using different techniques. So AWGN capacity is the largest. Then you have optimal power allocation. Which is greater than full channel inversion. Now, is truncated channel inversion better than full channel inversion or is worse than full channel inversion? I leave that to you. So once you know where to put truncated channel inversion in this inequality, then you can easily see which of the curves is for which capacity. Anyway, optimal power allocation is not asked. Well, this inequality tells you that AWGN is greater than full channel inversion. I have to put truncated channel inversion. Does it come here or here or here? Depending on that, you can answer all three questions. So find out where the capacity of truncated channel inversion lies, and you will be able to answer all three questions. Question 8. Consider a single tap channel of 20 kilohertz bandwidth with the following SNR characteristics. P of gamma 1 is 0.2, gamma 1 is 0.15, P of gamma 2 is 0.40, gamma 2 is 9, P of gamma 3 is 0.40, gamma 3 is 19. Find the ergodic capacity of the channel. I'll give you a few minutes. Try it out, and if you get the answer, put it in the chat box. I think we saw this in similar problem in last class. By ergodic capacity, here it's simply the average or expected value of capacity. So capacity is capacity we know per bandwidth, capacity per unit bandwidth is log 1 plus SNR. That is if there is a single signal to noise ratio, if the noise is not changing. Now there are three possible values for SNR. They're each occurring with different probabilities. So you can write down that the channel has capacity C1, which is B times log of 1 plus gamma 1 with probability P of gamma 1. You can write that for all three gammas. It has capacity Ci, it's, which is equal to B into log of 1, 1 plus gamma I with probability P of gamma I is equal to 1 to 3. Then the expected value is simply summation P of gamma I times Ci, where I goes from 1 to 3. That is the ergodic capacity of the channel. For example, if P of gamma 1 is equal to P of gamma 2 equal to P of gamma 3 equals 1/3, and B is 30 kilohertz, gamma 1 is 1, gamma 2 is 3, gamma 3 is 7, and C1 is B times log of 1 plus 1, log 2 is 1, it's B, C2 is B times log of 1 plus 3, which is log 4, 2B, C3 is B times log of 1 plus 7, which is log 8 is 3, so it's 3B. Now C is 1/3 of the time it's B, plus 1/3 of the time it's 2B, 1/3 of the time it's 3B. So this is should be 60 kilobits per second. In this question, the values are different, so you have to substitute these values and get the ergodic capacity. Question 9. Find the optimal power allocation P of gamma I by P bar for each SNR state of the channel distribution given in the above question. Okay. Um, Question 10 is also based on this. I'll do question 9 and 10 together. Question 10 is based on the optimal power allocation of the above question. Find the maximum capacity, that is when CSIT is available. So for, for these two questions, you're doing optimal power allocation. We're trying to get maximum capacity. For that, you have to do you have to use the water filling algorithm. And for that, you can go and see in the second lecture of week 9. Derivation is given where this optimal power allocation P of gamma by P bar 1 over gamma 0 minus 1 over gamma plus gamma must be greater than or equal to gamma 0. And in this case, since you have three different SNRs, the constraint becomes considering all three channels power constraint is summation for all three channels 1 over gamma 0 minus 1 over gamma I times P of gamma I should be equal to 1. So this 1 over gamma 0 is like the uh, total level of power, you could say, at which it sends. So to each of the channels, you are actually supplying 1 over gamma 0 minus 1 over gamma I, so that all three channels at the end are at a power of 1 over gamma 0. Now, if you put in the values So plug in the values of gamma I and find gamma 0. And you'll find out that gamma 0 is greater than gamma 1. Which means 1 over gamma 0 is less than 1 over gamma 1. So a water filling algorithm will be something like this. Let's say give you through a diagram to better understand. So if you have a tank like this and you start filling it with water, then initially the water will come and collect here. Then once it goes above this level, so initially the water is only on top of the middle block. Then the water starts getting on top of the middle and the rightmost block. Then once the empty gap is filled here, then water will start going on top of all three blocks. So we are trying to find now here in this case we are given gamma 1 is 0.15, gamma 2 is 9, gamma 3 is 19. So gamma 1 is less than gamma 2, less than gamma 3. So 1 over gamma 1 is greater than 1 over gamma 2, which is greater than 1 over gamma 3. So it's something like this. Let's say this is 1 over gamma 3. This is 1 over gamma 2. This is 1 over gamma 1. So we are trying to find some level 1 over gamma 0 so that the amount of extra power that you are allocating or extra water you are filling. In the case of the first channel, it will be 1 over gamma 0, 1 over, minus 1 over gamma I. Second channel will be 1 over gamma 0 minus 1 over gamma 2. For the third channel, it will be 1 over gamma 0 minus 1 over gamma 3. On average, the extra power you give will be the uh, probability P of gamma 1 times 1 over gamma 0 minus 1 over gamma 1. This will be P of gamma 2 times this P of gamma 3 times this. So this average value must is constrained to be 1. Actually, if you talk in terms of P of gamma is, then they are constrained by some power P bar, but we are taking the ratio P of gamma by P bar. So the ratio will be constrained. We are normalizing it in a sense. So the normalized value is constrained by 1. Now what happens is if this 1 over gamma 0 is below this 1 over gamma 1, let's say, then what you're saying is you're
supplying minus. So actually what we assumed was we had to supply 1 over gamma 0 minus 1 over gamma 1 to the first channel so that the overall level becomes 1 over gamma 0. But if your average level turns out to be somewhere here, that means you don't actually have to allocate anything to this, right? You can't allocate a negative quantity and bring down this power. 1 over gamma 1 is already there in channel 1. So that means you don't need to supply anything to the first channel. So that is what happens when you try to, when you put in the values in this equation and find the value of gamma 0, you find that gamma 0 is actually greater than gamma 1, which means 1 over gamma 0 will be lower than 1 over gamma 1. So that means you don't have to allocate any. This picture, earlier picture you drew was actually wrong. So you don't have to allocate any power to the first channel. So you're actually allocating zero power to first channel. So this is actually a contradiction. So no need to allocate any power to the first channel. That means using the first channel will actually bring down your capacity. So that means P of gamma 1 by P bar is 0. There are two options in 9 where P of the first power in the first channel is 0, right? So I've eliminated B and D for you. You have to differentiate between A and C. Now what you do is you don't allocate any power to the first channel. You allocate all the power to channel 2 and 3. Now the new constraint becomes, instead of I is equal to 1 to 3, I goes only from 2 and 3. 1 over gamma 0 minus 1 over gamma I times P of gamma I is 1. Now plug in the values and find gamma 0. And it will turn out that gamma 0 is less than gamma 2 and gamma 0 is less than gamma 3, which means something like this. It's 1 over gamma 0. Then the power allocated to channel I is P of gamma by P is 1 over gamma 0 minus 1 over gamma I for I is equal to 2 and 3. P of gamma 1 by P is already 0. Okay, I hope you understood. This is just this water filling technique. So initially you assume that once you fill all the power, so in this case, the volume of the water is analogous to the power. Once you fill up the power using this water filling technique, you assume this 1 over gamma 0 is above all power values 1 over gamma 1, 1 over gamma 2, and 1 over gamma 3. Then you find out how much extra power you have added to each other channel. So you should have added 1 over gamma 0 minus 1 over gamma 1. Then for channel 2, you have allocated 1 over gamma 0 minus 1 over gamma 2. For channel 3, you have allocated 1 over gamma 0 minus 1 over gamma. But channel 1 is used with probability P of gamma 1, channel 2 is used with probability P of gamma 2, channel 3 is used with probability P of gamma 3. So the average power of all three channels is P of gamma 1 into 1 over gamma 0 minus 1 over gamma 1 plus P of gamma 2 into 1 over gamma 0 minus 1 over gamma 2 plus P of gamma 3 into 1 over gamma 0 minus 1 over gamma 3. And this should be equal to 1. That is the power constraint. Then you find out the value of gamma 0. So you get the level at which your water is standing. If that level 1 over gamma 0 is actually less than 1 over gamma 1 or less than 1 over gamma 2, if it's less than 1 over gamma 3, then it's useless. No power allocation, that doesn't make any sense. No power allocation will give you enough SNR. All the channels are just useless. If it's below 1 over gamma 1, then you assume that you are allocating power, no power to gamma 1, no power to the first channel. Assume that you are only allocating power to channels 2 and 3. Then the extra power that you are allocating to channel 2 is 1 over gamma 0 minus 1 over gamma 2. Power allocated to channel 3 is 1 over gamma 0 minus 1 over gamma 3. Average is you multiply by probabilities, and that is constrained by 1 again. With that, you will get the new level of allocated power, which is 1 over gamma 0. Then you check for the new value of gamma 0 if 1 over gamma 0 is actually above 1 over gamma 2 and 1 over gamma 3. If it is not, then you have to allocate all your power to third channel and check if the power constraint is satisfied. In this case, the second step itself is satisfied, so you allocate 1 over gamma 0 minus 1 over gamma 2 to channel number 2, so that P of gamma I by P of gamma 2 by P is 1 over gamma 0 minus 1 over gamma 2. Similarly, P of gamma 3 by P is 1 over gamma 0 minus 1 over gamma 3. Okay, that's the power allocation you do. Next, once you do that, your capacity is B times. So there's no power allocated to channel 2, channel 1. So ignore channel 1. And you take the average capacity. So expected value of capacity we multiply by probability of gamma I times log to the base 2 of 1 plus 1 plus P of gamma I by P times gamma I, which will be P of gamma I by P was 1 minus gamma 0 minus 1 over gamma 0 minus 1 over gamma I multiplied by gamma I will get gamma I by gamma 0 minus 1. Is there's a 1 plus this, it will become P of gamma I times log to the base 2 of gamma I by gamma 0. Okay, putting in the values and calculating optimal power allocated and maximum capacity is left to you. Then question number 11, for the same channel distribution as in Q8, find the capacity with outage when CSIT is not available. Now here you have three different cases. Suppose you want no outage to occur, allowing no outage. Then since gamma 1 is the smallest SNR, we have to assume channel is always at gamma 1 and transmit. So outage occurs if you are transmitting below the SNR required. So since gamma 1 is the least value, if you transmit uh, without assuming any outage, then uh, you have to make sure that even if gamma 1 is the least, you are fine. So in this case, the capacity you can get is limited by gamma 1. It is B log of 1 plus gamma 1. Another scenario is allow outage whenever channel gain gamma is less than gamma 2. So suppose you are transmitting at some rate, and it turns out that the channel is in um, the first state, then it's okay if you are transmitting at a rate more than the allowed capacity for the first state. That case, outage will happen, but you're still fine with it. So you're saying if the channel state is actually state 1, then you might actually be in outage. But if you are in any other state, you won't be in outage. So in this case, the outage capacity is C is we saw this in last problem solving session also, B times 1 minus outage probability, and that is the probability that you're actually in state 1, so it's probability of gamma 1 times log to the base 2 1 plus gamma 2. So here you see, if you transmit at a rate greater than the capacity, then you will be in trouble. Another case would be allow outage whenever channel gain gamma is less than gamma 3. Now the outage capacity is B times 1 minus P outage log of 1 plus gamma 3. So here this will be P outage is probability that gamma is less than gamma 2, which is probability of gamma 1. Here the probability of outage is probability that gamma is less than gamma 3, which is P of gamma 1 plus P of gamma 2. So once again here the capacity is actually still calculated in the same way. Ergodic capacity C is summation P of gamma I times Ci is equal to 1 to 3. Except that since we are allowing outage and we are actually transmitting with a rate more than the capacity for gamma 1 and gamma 2, C1 and C2 is 0 in case 3. So in summation P of gamma I Ci, here C2 and C3 will be C1 and C2 will be 0, and in case 2 C1 will be 0 in a sense. Not exactly, but can kind of understand it in that way. Now you have three cases. What about case 4? Allowing outage at all possible channel gains. Does that even make sense? That doesn't really make sense. If you allow outage for any gain, then you can transmit at any rate you want. Because you can always say, I'm just in outage. What's the problem? So there are only three cases. One is you allow no outage. Second is you allow outage only if it is in state, the channel is in state 1. Three is allow outage only if it's in state 1 or 2. So now what you have to do is find out the actual capacity values in all three cases. Then compare which one gives you the best capacity. So this does not always mean that you will get best capacity in case 3, and that need not be true. Just because gamma 3 is greater than gamma 2 here, that does not mean this overall thing is actually greater than this. Because here there is 1 minus p of gamma 1 only. And here you are actually subtracting p of gamma 1 and p of gamma 2. So this term decreases. This term increases when compared to here, the case 2. So you actually have to find out the values and see which one is better. You can't directly tell. I hope you understood. Even if you don't understand, at least you have the formulas. So you have to compare, see in all three cases and choose the maximum. Choose the case that gives maximum capacity. Okay, question 12. For the channel distribution given in question 8, find the capacity when channel inversion is performed. So now it's not optimal power allocation anymore. It's not uh, capacity with outage. It's capacity with channel inversion. Next question is with truncated channel inversion. I'll give you 2 minutes. Try to solve this. I'll come back and give you the answer. Okay. So when you do channel inversion, the capacity with channel inversion is C equals B times log to the base 2 of 1 plus sigma, where sigma is 1 over expected value of 1 over gamma. Derivation for this you have to go and check in the lectures. And expected value, since we have three channels, it's sigma is equal to 1 to 3, probability of getting gamma I into 1 over gamma. Here you know the value of gamma is, so you can simply find capacity. Then for question 13, for the channel distribution in 8, find the truncated channel inversion capacity. So similar to this outage question, here again there are different cases. First is considering all the channels, C is capacity obtained in question 12. Then you consider the two best channels. Now sigma is, you discard the first channel, I is equal to 2 to 3 p of sigma I times 1 over sigma I. Then again C is 1 minus p of, sorry, did I say sigma? Gamma I. P of gamma I times 1 over gamma I. 1 over gamma I. Again 1 minus p of gamma 1 times b into log of 1 plus sigma. Then consider the best channel. Now again you have to Discard the first two channels, so you simply get P of gamma 3 into 1 over gamma 3. C is 1 minus P of gamma 1 minus P of gamma 2 times B times log to the base 2 1 plus sigma. So again, you have three cases. You have to find the capacity in all three cases. Choose the best case. All right, that we solved this question. But one more thing you do is we have calculated the capacity. First, we found the ergodic capacity. Then we found capacity using optimal power allocation. Then we found the capacity with outage. Then we found the capacity with channel inversion, full channel inversion, and capacity with truncated channel inversion. So we actually found all the capacities that we were looking for in question number 5. In that, while solving that question, I had given that AWGN capacity is greater than optimal power allocation, which is greater than full channel inversion, and I told you to find what is the capacity with where does the capacity with truncated channel inversion fall. So since we have calculated optimal truncated and full channel inversion capacity, you can use the values in this scenario also to find the trend there. So once you calculate the optimal power allocation, um, find out whether it is greater than or less than the um, truncated capacity, and find out whether the truncated capacity is less than or greater than the capacity with full channel inversion. Those three will follow the same trend in question number 5 also. So if you solve 6, 7, 8, 9, you can solve 5 also. Except that the ergodic capacity doesn't exactly match with the AWGN capacity. Okay, we have completed all the numericals. Question 14. What are the features of having multiple transmitters and receivers in a wireless system? So we already seen in previous lectures that you get diversity benefits, and we saw in, you can go and look in question 1 where you had L receive antennas. Once you solve that, you will know whether you got increased capacity or decreased capacity by adding all the signals at the L receive antennas. So from that, you can find out whether having multiple receive antennas actually helped you increase your capacity. So from that, you can hence tell whether 14B is true or not. 14C also we saw in previous class, uh, the Alamo T code, which allowed spatial and temporal multiplexing. So all three are actually true. Then in question 15, which of the following statements are true? Statement 1, the water filling strategy is more power efficient than channel inversion. Statement 2, water filling is suitable to channels that experience fast fading. Statement 1, we already saw in the on these questions where we actually found water filling is optimal power allocation. Uh, so we found the capacity of optimal power allocation and we found the capacity of channel inversion. So from that you can see which capacity is greater. From that you can tell whether statement 1 is true or false. Statement 2, whether it is true or false, you can see, can't directly tell, but you can tell from the example here. The SNRs are actually changing a lot. Statement 2, you have to check. Statement 1, we already saw from the problems. Then question, Question 16, you have to allocate power efficiently for a fast fading frequency selective channel to maximize throughput over a long period of time. All the while you are heavily constrained by power. Which of the following will you choose? Water filling over time and water filling over frequency, both A and B. So since channel is fast fading, the SNR will change very rapidly, instantaneous SNR. Thus, it's changing with time, so you need water filling with respect to time. And the channel is frequency selective. So it's a fading, fast fading frequency selective channel. So you need a water filling solution uh, to select which channel you have to, which of the frequency channels you have to transmit over. For both time and frequency, you have to do a water filling algorithm. Then question 17, the lecture it was shown that using DSSS increases the bandwidth of the signal. What is the consequence of this increase in bandwidth? Since bandwidth increases, time resolution becomes smaller, and as time resolution becomes smaller, different multipath components can be distinguished. Once you can distinguish different multipath components, you can use MRC. Then question 8 is statement 1 says DSSS increase the bandwidth of the signal. So already in 17 we saw in the lecture it was shown that using DSSS increase the bandwidth of the signal. So from the question in 17 itself we can tell statement 1 is true. Statement 2, DSSS doesn't alter the magnitude of the frequency response. So statement true, I'll leave it to you. Statement 1 is true. So either option A or C. And in 19, in CDMA, multiple users can occupy the same frequency bands at the same time. So your CDMA is code division multiple access where different users are communicating using different codes. Since they have different codes, these codes are orthogonal, so you don't need to distinguish in frequency between two users. The code itself will do that. Then, which of the following are spread spectrum technologies? That you can just theoretical question, you can answer it yourself. Oh, there are still numericals. Question 21, I won't write the questions. Uh, I think they are similar, same as assignment questions. Spread spectrum communication uses chips for their transmission and reception of signals. You have a modulator with a chip duration of 1 microsecond. You are transmitting, so given modulator with chip duration 1 microsecond, you are transmitting a signal with a signal symbol rate is 62.5 kilobaud. What is the spreading factor? To find spreading factor, Spreading factor is symbol duration divided by chip duration. Chip duration is 1 microsecond. So if you write the symbol duration is in microseconds, then you'll get the spreading factor. That is the spreading factor. So the symbol duration is symbol rate is 62.5 kilobaud. So a baud is one symbol per second. So 62.5 kilobaud is 62,500 symbols per second. So in 1 second, you're transmitting 62,500 symbols. So symbol duration is uh, 1 over 62,500. That will be in seconds. So you have to convert to microseconds. Then divided by chip duration, which is 1 microsecond. Then you'll get the spreading factor. Next, you have one more numerical. I'll skip this question based on the graph of the spectrum. All I can tell you is that so spreading factor is 16. So if the um, oops, I should have said that. Okay, you found the spreading factor in this question. I use that spreading factor. Let's say it's A. So if the first zero crossing point in the spectrum before spreading is at point X in the X-axis, then after spreading by a spreading factor A, the first zero crossing point will be at A times X. And then, so that will give you which of them has, so from the zero crossing point, you can identify, but yeah, just from the zero crossing point, you can identify. One more factor is that the magnitude is attenuated. Well, that answers 18 statement 2. DSSS doesn't alter the magnitude of frequency response, but you can see in all the options that the magnitude is actually attenuated. So from this you can answer statement 2 in 18, even if you don't know the answer for this question number 22 itself. And finally, I'll simply give formula for question 23. Consider two users simultaneously transmitting to a single receiver in a DWGN channel. This is a typical scenario in a cellular system with multiple users sending signals to a base station. Assume the users have received power of, there are two users and single receiver as the AWGN channel. Assume the users have received power of 10 milliwatts and 14 milliwatts. Total noise at the receiver in the bandwidth of interest of zero point 0.1 milliwatts. The channel bandwidth for each user is 20 megahertz. Suppose that the receiver decodes using user 1's signal first. In this decoding, user 2's signal acts as noise. Assume it has the same statistics as AWGN. What is the capacity of user 1's channel with this additional interference noise? So we know C is V log of 1 plus signal to interference noise ratio. Earlier we had only noise limited system, so it was SNR. Here we have one interference, so it is SINR, where the SINR is the transmit power divided by interference power plus noise power. So here user 1 is the transmitter. So he is transmitting, transmit power is 10 milliwatts. User 2 is interferer. So interference power is 14 milliwatts. Then noise power is zero point 0.1 milliwatts. So you substitute those values, you get SINR. And the capacity is bandwidth is same for both of them, 20 megahertz into log of 1 plus SINR. Okay, this is user 1, user 2, this is noise. All right, that concludes this week's problem solving session. I hope it was helpful.